So the arts of container security are nowadays well known by many people, but what are the actual things you need to know about containers? Because it's coming a long way and it dates back to the kernel source itself, right? So on the container security field, you need also to learn about kernel internals a lot. And this is what we want to deal with you today. So during your seasoning or during your graduation towards the higher levels of container security, you need to start with basics, with the white belt. So, of course, we are talking about many flavors of containers in the field. Maybe you're dealing with Kubernetes in your actual work, and Kubernetes creates containers, right? It runs containers, manages it. That's all second nature for all of us, right? Nothing new. But in the end, we're talking about the nodes. So these Linux servers executing our containers, executing the Linux processes. And here we want to dial into the depth of the container security on the Linux servers. This is nothing different, or not a lot different in Docker. So if you deal with Docker security, you have the same problem. You want to secure your Linux processes just with another orchestrator, right? With another thing that manages or executes your containers or schedules your container creation. Again, you have Linux processes. We all know that. So that's for the white belts to know as well. And if we go further, of course, we can uncover the management, which is more or less the containerd and the process itself we're talking about today. So we're dealing with those little parts here when we talk about the confu. The white belts also need to know what are the little pieces that operate your container, which is, of course, the namespaces, which is more or less views on processes and the actual mounted file systems, and the control groups, which is more or less resource management. Blah, blah, blah. You all heard about this many times, but to reiterate on some of the specific things, we want to have a look especially on the namespaces, and we want to have a look on how the process is configured, which user IDs it has, which capabilities, so which parts of the root it has. And the white belts also need to know what can they do after the game code execution on the system. And maybe you had this at the famous XZ attack, where one of the processes is going rogue and executing another attacker code, which is more or less a process again. This should be found on clusters as well as Docker clusters. But in the end, if we have a container, we need to know what we can find. And of course, you usually have a networking infrastructure on it where you more or less have one virtual cable pulled from your Linux server, from a node into the container. And of course, you need to see what you can find within. And usually that's your keys as well as your identities, right? That's what we're looking for if we talk about containers. Sure, this is not all, right? So maybe you want to break it. I won't break it now. But the actual question here is, to know confu, we want to also break the container. The question is, in which circumstances we are able to do that? Because we don't want to hurt our hand, of course, as we break it. because many people are employing hardening techniques, such as capabilities, which is more or less the little pieces again of root, where we say, okay, this container is able to write everywhere in the file system to install something, maybe during build processes, right? You need that. You don't want to be hindered installing things. There you need to have, for example, the capability deck override to just write everywhere. And you want to maybe bind a service. You also know that, which is the CapNet bind service. And of course, for proper container configuration, you want to have clean images with nice and well set permissions, of course. We all do that. And going further, you can employ, for example, mandatory access control. But in the end, you do the same thing over and over and over again, right? So the question is, when can we break it? And usually a very well starting point is to have a quite capable user ID, which is the root, the zero user, as well as the capability sets that are not so often seen in this case in real containers. Usually that's tracked down to a very low limit. And if you have that, you can scan around your container and pull out the secrets. And what a white belt also needs to know is, of course, nowadays, eBPF, right? That's why we are here. And eBPF, and who wrote eBPF here, which is my question here, and who, okay, 2 people, that's good, who already did some work with eBPF, like looking through documentation. Okay, that's cool. For all others, it's, again, your JavaScript for your kernel. So you don't want maybe to load a kernel module. You just want to load something different that does more or less similar things. So you can write code and load it into the kernel after you compile it. And the kernel makes sure that this gets executed to the points you attach it. Meaning, if you write something like this, which is just code that prints the current process which is executed or scheduled for execution, we attach it to a specific point, and it's the first line here. We attach it to a trace point, meaning the kernel executes this program every time the kernel schedules a program, which is nice because if you want, for example, find attackers and they execute their own attacker code, you can watch for that. And you can watch it from a kernel perspective and not only a user process, which is quite limited, right? So what are the attachment points? And if you not come across that, I just list you some of those, but to sum it up for you in 3 things, it's about networking. So every time a network packet comes in, every time, for example, a socket wants to read from the network, then this can jump in. You can also deal with system calls, right? For example, as you write the file or open a file, you can wait for that. And you can deal with trace points. So you can, for example, wait until the kernel says, hey, there's an event going on, and you can jump in. Of course, there's more on that, but to sum it up simply, that's the areas you want to deal with. All right, so what can we already, or what's already there? So if you never used eBPF before, I would consider, or I would argue, you did use it. Because as your Linux system starts, the systemd already loads an eBPF program for you. And as you create a new container with Docker or also with Kubernetes, also eBPF programs are loaded on the fly. And those are guarding your devices on the bottom, right? Your disk, for example, or your flash memory on an embedded device, or whatever a device interface has. This program jumps in and says, hey, that's okay that you read and write from that, or that it denies the access. And that's really, really important because there are many breakouts because of that. We will deal with that again. And of course, we're dealing with white belts here. The white belts need to know what privileged containers are. And usually we don't like them because they have all the good capabilities to reiterate the good capabilities. So the good settings for root. And they circumvent this eBPF program that guards your devices. That's not loaded in this case. And of course, you can administer the network and, for example, create monster in the middle scenarios. So again, this is second nature for all of us. Let's deal with more complicated stuff, right? Because you know, no Kung Fu now. So to earn your higher belts, you want to deal with the details of each and every capability and each and every system call, right? That's quite tedious. To sum things up for you, one problem with quite capable containers that, for example, automatically on the fly load drivers, your kernel modules, those are quite nasty, because if you get control over one of those, which sometimes you find this when you, for example, need to load another driver on the fly, then you have maybe the cap sysadmin capability, so the ability to do that, right? So the container can do that. And this could more or less tear down a node. How? You, for example, load a little driver on your own, because you're now capable to do that. On the top, we ensmodded it, and this changed the behavior of our system. In this case, it created a new process in another namespace, which is the root namespace. And now you can control it via a socket. And this is quite neat, because you can now jump from a container out to the main system. This is more or less the code you need to write. It's super easy, right? So you just write some things like you want to create a new user process in the user land, and you load it. It's a bit complicated with this kernel header stuff in real practice, but in the end, this is one of the ways to jump, for example, from a container outside to the main machine. All right, what do we have else? What about this? So we want to look around in a more privileged container. And in this case, we have the capabilities also to deal with a proc file system. So why is this a thing? Usually you have also maintenance and like attestation or information gathering containers in your cluster to collect information. What are the processes doing? How much data do they consume? How much computing power? And one way to do it is to expose the nodes, so the Linux servers proc system, which is more or less the view of the kernel, so how the kernel views the system. But there is a catch here. Because here you see you have mounted the host proc, so the proc system, the /proc, into one of the containers. And now we do this little trickery here. We search for every process, right? for every file descriptor any process has. And if this is a directory, we can do something. This is quite similar to this leaky vessel attack, if you came across that. It's also dealing with file descriptors and leveraging those file descriptors. And this is how you more or less find them. You just search for them. And after that, let's proceed here. You indeed find a directory file descriptor here, which is on the Linux server. And now something weird happens. This file descriptor is, for example, on a control group, which is not really important at this place. But if you do this little ///, maybe you did this before, this traversal attack, this doesn't feel like a file system here, right? Because it doesn't feel like a proc anymore. It more or less feels like a different, like traversing out of the system. And here we see again, after we traversed up to the slash, we just change root and we're out. Boom. On the bottom, we're on the node now. And sometimes you find this because it was not protected enough. Nowadays, you need a special capability for that. So you have this capped ptrace capability. You need to do that, but this is more or less details. But always in your real life, if you have to deal with track, be very careful with that because this is a source of many, many problems. What about bind mounts? What are bind mounts? We want to, like the example before, we want to take proc and bind it into the system, right? We want to give the container the ability to view it as it would be in his own or its own file system, right? That's the thing. What's the problem with that? If you bind mount the wrong thing, you screw the node. Not the cluster maybe, but it's a good starting point to attack the cluster as well. This became very popular with the Docker and Docker scenarios. And my question would be, who uses Docker and Docker in the builds pipelines? Because I found it quite several times in my day job is more or less attacking stuff like this. And if you do that, so thank you for exposing this, but if you do that, maybe you want to have a look how the socket, how you communicate with the Docker engine is exposed. Because the problem is if you bind mount, for example, root into your container, in your build container, and there this build stuff is going on, and the other containers have access to that, they can also ask for creating another container, right? And if you have Docker and Docker, I would say I would ask for a very privileged container in this case. And because I have the access to the socket, this would work. This is nothing new, but sometimes we can find this also on scenarios where we have a little cluster and there is no Docker involved anymore, right? In Kubernetes, it's thrown out, but the container D is still there. And there's this little control command that also can talk to container D, and it can also ask for containers. It's a bit messy because the user interface is not really intended for everyday use, and that could be very problematic. But if you look closely here, you can do the kung fu. So you just say, hey, have your images here. If not, pull all the images you need, because that's not automatic like in cool Docker or Kubernetes. And after that, we say, hey, we want to create a new container privileged with the host's network and jump into that, and boom, you have control over the network of the server as well as the file system. You can just do the same change root trick again. So this, keep in mind, if you expose sockets that could be leveraged. In every martial art, there's also this thing, how you stand correctly, right? Is it like this, or like this, or like this? This is the same thing. If you change the posture of your containers, this could drastically change the posture of your security in whole, right? All right. What else? Now we can finally approach the master, right? Not me, but I'm still learning. If you look closely on the color, still learning. And also it matches the color scheme, but that's a different thing. We could also learn from the masters of eBPF, which is more or less the people who created this stuff, and also learn about the ancient scrolls of man pages and kernel documentation, because there the information already lies how you can use eBPF also for offensive purposes. We heard about eBPF that we can use it for defense, right? If we want to protect our file, our disks, for example, our hardware, eBPF came quite handy for that. Now we can also use it maybe for offensive purposes. And there we need the kernel probes, which is already there. That's not eBPF. It's eBPF related, but it's not origin from there. We will also leverage the tracing of the kernel. And a little exercise here is on the left. We have again a little eBPF program that maybe I already showed it in some other talks, but please bear with me. If we want, for example, to protect our system from a specific process name, we can do this here. So we can say, hey, every time here, we do the comparison, every time a process is scheduled for execution, as we have seen in the first slides, every time we want to grab that and decide. And here we say, if it's a cat, kill the cat. Let's see if we can kill the cat. Boom, boom. So here we say on the right, finally, hopefully, on the left, we load the program. So now we took the eBPF program and put it into the kernel and attached it to the tracing point. And you already see, hey, you can't use cat anymore on the system without touching anything else. And this could be becoming quite handy for an attacker, because now he or she can hinder you from defending your system, can interfere what you can do on the system just by loading an eBPF program. And maybe you don't see that because it's just loaded and it's underneath you and it's in the kernel, and you just see, hey, things are getting messy. After you unload it again, everything is back to normal. Okay, what else? And the answer is, of course, you can mess with the network. You can say, every time a network packet comes to you, you can say, this time you don't like it. And you can jump in at a specific point, which is, for example, the express data path. There are many talks around this topic, so I will use it quite shortly. In this case, in the containers, you more or less attach your eBPF programs on the interfaces, on your virtual interfaces in the containers, or as well as on the host. And every time, for example, network packets gets received, you need to do the fancy parsing of your network packet to find out, okay, is it TCP or is it UDP or is it the right port? And after that, you can, for example, throw it away. if it comes from a defender. So you can just jump in with the eBPF program here. But what if you ban the reality of the Linux host itself? So you need to more or less then dig into how files, for example, are processed, meaning you just say, hey, on the left, you have a Linux user space program. On the right, you see what the kernel does. And you want to learn what is done. And then you look at the source on the bottom and say, hey, there is the processing done. Maybe I want to jump in there. And after that, you just go through the whole processing, which is a bit tedious, I have to say. But bear with me. After you identified the actual functions that are used and you understand how they are used, you can create a more complex program that says every time a file is opened, you want to get the file descriptor, and then you identify, is it the right process you want to interfere with? And then you more or less juggle this around it with a little side memory, which is the maps. And after you did that, you interfered with the system and how the system processes it. So let's see it in action. Boom, boom. So on the left, I have a little container which has more or less, let's see, little to none capabilities. And we have a little SSH connection to the node, which doesn't work because we don't know the password. On the left, again, we do the same thing. We don't know the password. But if you're able to load eBPF programs like this into the kernel, you can change how the kernel processes it, the files. And those are the loaded programs I put in. And after that, we just, for the sake of it, try to type in our password. And we finally root inside the container. What? How? So the thing here is, after we typed in root, we have better capabilities. And we can even log onto the node. But what happened in the background? What we did there is, every time if the file shadow, which more or less contains the hash of your password, is read from the whole system. And you can load this eBPF program from the container. So now for the whole system, we change the processing. And if you look closely, a little bit later, you see if I cat the etc shadow, you see the first line I, on the fly, changed with my eBPF program. So the processes ask for, hey, I want to read shadow, and I more or less say, hey, I jump in. There is my shadow for you, and the first line is root. You're asking for root, so that's fine. The rest, unfortunately, I corrupted it. Sorry for that. So I'm not. Didn't have much time, but for an attack purpose, that more or less works. And in the end, you're able to change how the system perceives a file, and you can scope this also to a specific process or container, for example. So there are some things up here. This could really change how we perceive our Linux system and how we can trust on information we ask from the user space. This is built on research that has been also published some years ago. So that's nothing new. But keep in mind, if you have come across eBPF, that I think now is a good time to start. We also, with Dimi, and Philip, we do nice little meetups for the topic. So feel free to come. And you can also look at the resources. Some of those are really interesting. So you can see how offensive eBPF is already put into place many years ago. And security tools already use it heavily. So if you have one of those, you can be sure that you use eBPF. The question, of course, is this Kung Fu tough enough to kill Bill, the bill of behavior, which is presented in the other track? I think the research from Constanze, which is also key researcher at SB Research, is really heading into the right direction for seeing and testing what the system should do. And if your system deviates from that, you can react. Just a side note. Summing things up here, thank you for your attention. And maybe we are the one for solving the eBPF problem. And again, if you have any questions, please reach out to me. Thank you for your attention again.